Starting streaming. So coming to you live from my basement again, because it's still not even 0 degrees outside last I checked. So thank you for all being flexible to meet this way. I think it's in our best interest to not have frostbite. That's the irony, of course, is that, it's the college students who are walking long distances and waiting for buses, and the university is like, good luck. But all the little kids are the ones who get the breaks. So I care about you guys too, and I care about myself, quite frankly. So we were talking about, regression type models yesterday. Before I dive back into where we left off, does anybody have any homework questions that I can address first? No? Okay. Then after class today, once I verify that everybody was able to log into the homework system, I will put up the homework that's going to be due next week. It's just going to be literally what we're going over today. It's intended to be pretty easy. It's supposed to be just a review of concepts in regression, how to interpret slopes and that kind of thing. So it shouldn't take very long to do it at all. I will send out an email once that is ready for you to give it a shot. So where we left off yesterday, let's see, we were talking about sort of the overview of what's new and what's not new. I think we're here on slide 16-ish. So yeah, we'll start there. 13-ish, I think that'll work. Okay, y'all with me?
Yep. Yes.
Excellent. Okay, so the big picture here is that we're starting off with just a review of general linear models, because a lot of the same concepts that you've learned in terms of how to interpret intercepts and slopes are going to recur in the longitudinal models we're going to get to. So I find it useful just to go over familiar models, make sure that we all understand the terminology that we're going to be using to talk about those, as well as the software. So I'm going to give you an overview of how to do general linear models today using Mixed in SAS. It's the exact same package as you can use Mixed in Stata, as in SPSS. I think Elmer would have a lot of the same options and things like that. And the reason that I like to do these regression type models in Mixed, even if I don't necessarily need to, is because Mixed has additional options that make life easier for me. And so that's what the list here on slide 13 says. You can request any type of model implied fixed effect. So that's super handy when you're doing interaction terms, but it's also handy when you're trying to get conditional means or intercepts. I will show you how to do model comparisons in a more general way, besides the special cases that you probably have seen before. This same routine then and these same benefits can be used to analyze any kind of univariate or multivariate outcome that is supposed to have normal residuals, and so that will extend into longitudinal and other kinds of multi-level models. And these same software techniques in terms of how to get the output that is of interest to you readily extends to nonlinear types of outcomes as well, so binary, count, etc., etc. So the take-home message is that we're starting from models you know. The software looks a little bit different, and some of the options for how you ask for things looks a little bit different. So we're just working with that before we move on to models that you don't know. The main difference in what you're going to see for output is that the algorithm that is going to be producing the results is likelihood estimation. And yes, we will talk more about that. But what it means practically speaking is that some of the summary information that you're used to seeing, such as sums of squares and expected mean squares, aren't going to be on your output anymore, because that's not how it works. I had a question after class. Who was it that was asking me about how minimizing sums of squares and maximizing likelihood is actually the same thing?
Oh, it's me.
And
It's
who?
Ninja.
Oh, say who's me?
Oh, yeah.
Ninja the ninja?
Yeah.
Okay, so and I had suggested to her that if you're
Oh,
one of
yeah.
those people who likes to see the math underneath these things, there's an Enders chapter that's coming later in your reading list that you would want to refer to now. I want to say it's chapter 4. It might be 3. where he shows how the result in terms of the mean and the variance that would maximize the likelihood in summarizing a normal distribution, how that same result has a computational shortcut that comes about through minimizing the sum of squared errors. So in a one limited case, you get to the same place sort of two different ways because of some shortcuts to the calculus involved. But when that one special case isn't applicable, so when you have some other type of distribution you're working with, when groups have different variances, when you have more than one kind of variance, any of those complicating factors, then likelihood estimation is the way to go. So I found that helpful to look at, and that might be helpful to sort of see how these things are or not the same. But likelihood estimation via REML, so that's residual maximum likelihood is what it's called, or restricted maximum likelihood. It's known by two different names. That is the same thing as least squares if you have complete data. So it's not anything new and different. It's just generalizes to something that's more flexible when you need it to be. So, okay, questions on any of that before I keep going? No, we're good?
Yep.
Good. All right, thank you. All right, so then just reviewing. How do we talk about making decisions about what kinds of effects we want to have in our model? Typically, it's the logic of significance testing. So when you're talking about the model for the means, so we're talking about fixed effects of predictors, effects that everybody gets in common, there's going to be 4 or 5 pieces of output that you want to pay attention to. There's the estimate. That's the answer. That's usually in the first column. So that's the numerical quantity that gives you the best guess that parameter is, so the intercept or the slope. Next to that usually is the standard error, and both of those things are things you would want to report in any manuscript or result section. The standard error indexes the precision, so smaller standard errors mean that the model is more likely that that estimate is the best version of itself. If you take that estimate and divide it by the standard error, that ratio then either is characterized as a t-value or a z-value. And that depends on your software and whether or not you're using denominator degrees of freedom. So I have a slide on this in just a second to illustrate the differences in what you get. Then based on the value of that t or z, you end up with a p-value, which is the last column usually, and the column that we're probably most used to paying attention to. And so this procedure, this idea that you take the estimate divided by the standard error and that ratio forms a t or a z, that's what's known as a univariate Wald test. The term Wald is traditionally used for z's specifically, but if you use a t instead, I think it's fair to describe it as a modified univariate Wald test. And so this is the procedure that you're used to using for regression type models. This is the exact same procedure that we're going to be using for longitudinal models. I just wanted you to know what it's called. That way, when you talk about how you assess significance of your fixed effects in manuscript, you can say, I used a univariate Wald test. Whether or not you get the t or the z then depends on your software. So this is something I discovered too late, so I wanted to give it to you right away. The idea of how many different terms you're testing at once is what delineates the rows in this table on slide 16. So if you're testing one thing, for instance, one slope for one predictor, then we would say that the degrees of freedom for the test has a numerator of 1. So that's where we fall into the category of univariate Wald test. Now, whether that estimate over standard error ratio is described as a z or a t depends on whether or not you're using denominator degrees of freedom, which you're supposed to use whenever you have a small-ish sample. And I think the limit is usually described as somewhere around 30 where this starts to matter. So if you're assuming that you have no denominator degrees of freedom, if you're not using it at all, then basically you're saying you have an infinite sample, and that gives you a z. So if you have software that does not report degrees of freedom of any kind, such as M+, and sets as the default in Stata, they're calling it a z. So the estimate over the standard error, they're treating it as a z, and that's where the p-value comes from. If instead you have some kind of degrees of freedom being reported, then it's using that and the ratio is a t. And there's different ways of estimating denominator degrees of freedom in longitudinal models, and some are better than others. The reason that you have to estimate it is because it's not clear what it should be when you have a sample size that's not only different at each level, but it's also different across each level 2 unit. So if each person doesn't have the same number of observations, right, then what should the degrees of freedom be? So there are debates about this, and the options that are available in software packages I have as the last row here. There's a reason why I tend to report Satterthwaite in the book and in all of my examples is because that's the one that's used most predominantly across SAS, SPSS, and Stata, which are the packages that I usually try to teach in. SAS and Stata also have a few others. KR stands for Kenward Roger. It's the last names of the dudes who invented it. That's supposed to be extra good in extra small samples, but it's not available in SPSS. If you have enough people, KR becomes Satterthwaite. And all of the descriptions of these things are in Chapter 5. But I just wanted to introduce you to the broad distinction now. If you have denominator degrees of freedom that's not infinite, then you're using a t. If it's assumed to be infinite, you're using a z. And that's if you're testing one thing at a time. If you're testing more than one fixed effect at a time, then that's what's known as a multivariate wald test. So your numerator degrees of freedom is greater than 1. Then instead of z, you have a chi-square to report. If you're using a t, you have an f report to report, because z squared is chi-square and t squared is f. So you will see these letters being used across different packages, and it ties to whether or not there's denominator degrees of freedom. And multivariate wald test is something that I think people have less experience with, but it's something that we're going to use fairly frequently to be able to answer more complex types of research questions. So, okay, questions so far? Is this stuff new or is this stuff old?
Recent, let's say.
It's what?
Let's say recent, just last year.
It's recent?
Kind of, not too much. Old and recent, just last semester and last year.
Okay.
May I have a question?
Yeah.
So, I remember there is the Hollington's t-square test in the multivariate methodology. So, I mean, I'm not sure like whether it's like how to that which category will that go to, or it's different animal.
I'm trying to remember what that is used for. Is it some kind of model comparison with non-nested models?
It's like when there are multiple outcome variables.
Oh.
So here we have one outcome variable.
I see. That would probably be closest to the F column here, the F cell.
Okay. Oh, okay.
Yeah, since t squared is F, I'm not sure why they would call it t squared as opposed to F. I would have to look up that. But that would be sort of when you're testing more than one thing at a time, and you have some kind of denominator degrees of freedom.
Okay. Yeah, gotcha. Thank you.
Yeah, and by thing, I mean fixed effect. Sorry, I need to be more specific. Yep. Okay. All right. Any other questions or clarifications? Okay. So then where does the standard error come from? Just a review, because this topic is going to become important when we have models with more than one kind of error variance in them, which is anything that has more than one dimension to sampling. So the basic formula for a standard error in a single level model, like a regression, is that it's the square root of the residual variance of y divided by the variance of x times the sample size minus the number of fixed effects in the model. So all things being equal, if you have less variance left over, then your standard error is smaller. If you have more than one predictor in a model, so it's the standard error of a fixed effect among many, then the denominator also has to factor in how much variance of the predictor there is that's unique relative to the other predictors. So the numerator then dictates, is a reflection of, I guess, how good the model is, in the sense that better models have less variance left over. But it also then is important what variance is counting in the numerator. So we'll see this in our one of our first examples with longitudinal data. If you have data where you have level 1 persons nested within, level 1 occasions nested in level 2 persons, right? You have variance over time, variance across people. If you're testing people things, both of those variances are relevant. If you're testing time things, then only the time variance is relevant. So if you have a multi-level model that understands which variance is relevant in testing which fixed effect, your standard error is going to be different than if you ignored the multi-level nature of the data and just stuck all of the variance up in the numerator. The other thing to keep in mind is that the significance of a given predictor can change later on in a sequence of models than earlier on. So if you test a fixed effect and it's not significant, and you enter a bunch of other predictors that do a much better job of explaining variance, that same fixed effect can become significant later on if the variance has been reduced. So that is to say, there's never sort of a unilateral decision that one could make, because everything is conditional on the state of the model at the point at which you evaluate a new predictor. But smaller standard errors mean that you're going to have a more significant, I'm doing air quotes right now, p-value. So special cases of this idea of testing multiple parameters at once. The two that I'm guessing you're familiar with that I can think of most readily is in the context of an ANOVA for the first one, an omnibus F-test, or the context and a hierarchical regression for the second. So have you guys had ANOVA presented to you in a course before?
Yes.
Yes. So there's a phrase that I grew up with in these classes known as an omnibus F-test. Is that a phrase you know?
Mm-hmm.
Yes.
Yeah, so it means like an overall. So if I have, say, a 4-group variable, and I want to know if the means are different across my 4 groups, one of the pieces of output I would get is what I would call an omnibus F-test for the effective group. And if I have 4 groups, how many degrees of freedom is that test?
3?
Yeah, 3, exactly. So that's numerator 3. So it's the idea that you're testing 3 things at once. It's a multivariate Wald test. It's an F because you have some kind of denominator degrees of freedom based on your sample size and the number of fixed effects in your model. The same idea gets a different name in the context of regression. So if you fit a regression model, you have more than one predictor, one of the pieces of output that you get is an F-test for the model R-square, right?
Mm-hmm.
And that's the significance of whether that R-square is greater than 0. That's the same idea. If you were to add new predictors in a second step, and it gives you a separate piece of output for each step, in addition to the test of the R-square, you can ask for a change in the R-square test, and that's an F as well. So those special tests are provided by default. I will teach you how to ask for them for those cases, as well as for any case under the sun in which you're interested in testing more than one effect at the same time. This shows up in longitudinal modeling pretty frequently because it takes more than one effect to sometimes describe the pattern of that would answer a hypothesis. So just as an example, let's say that I have a longitudinal study in which I simply want to know, did the outcome change over time? Let's say it's beginning research. I don't even know if the outcome is supposed to change. And I find that there is a non-significant linear change coupled with a significant quadratic change. That could happen. If I want to answer the general question, is there significant change? Another piece of output that I can give them is the 2-degree of freedom test for the linear fixed effect of time and the quadratic fixed effect of time put together. That then would answer the question more directly, is there any change over time? It takes 2 parameters to describe it, but those 2 parameters then equal the thing that I want to know about. You can also have a predictor have an effect on the intercept and an effect on the slope. You could test both of those effects together using this type of multivariate wald test. So you've seen this before. It's just that this is a more general technique that I want you to be able to have in your toolbox. And what it will look like in code is down below here. Let me get my cursor. Let's see. Here we go. So this is an example using SAS procMixed. It's going to look fairly similar in any other program. So this is your very first introduction to procMixed. Data equals tells it the name of the data set. Method is going to refer to whether it's using REML estimation or regular flavor maximum likelihood. REML is the default, but I have it here just to make the point that this is the same thing as a regression model. This is least squares. Model, then, is outcome equals fixed effects of predictors. So in this case, my outcome is called Y. I have 2 predictors, X1 and X2. The default is that these predictors are treated as continuous. So I'm asking for a slope relating X1 to Y and a slope relating X2 to Y. And each of their univariate effects in the output would be its effect after controlling for the other. The contrast then is the new part that I wanted to show you here, how to ask for a joint test of X1 and X2. So in contrast, you have to give it a label, which is nice because that's your trail of breadcrumbs to keep track of what you're doing. So this is a 2-degree of freedom f-test, and you list the parameters that you want to test. So in this type of SAS code, when you list x1, what you're actually listing is its beta. You're referring to beta 1 in the equation here when you list x1. Similarly, when you list x2, you're referring to beta 2. So you're asking for a joint test of beta 1 and beta 2 where it understands that it's supposed to be 2 degrees of freedom because you've separated these with a comma. So then, given that x1 and x2 are the only predictors in this model, functionally what I'm doing is testing the significance of the model R-square. Together, do these predictors reduce Y variance? That's what I want to know. Does that make sense?
Yes.
Yes? Okay, one person thinks it makes sense. That's a good start.
Yes.
Yes?
Yes, that's
Okay. All right, that's good. That's good. In putting effects of the predictors in the model, though, I am all about the centering. This is sometimes not even taught. I tend to be much more gung-ho about this than other people because I live most of my life doing longitudinal data analyses. But the reason that some people don't necessarily care about this is because choices that you make for centering, when you're centering with a constant, meaning that every person has the same value subtracted or added to their predictor, it doesn't change the model in the sense of variance accounted for. It doesn't change the model predicted outcomes. What it does change is what the intercept means. And so you can end up with intercepts that don't make any kind of sense if you don't have a centering point for your predictor that is in the scale of the data, so 0 has to mean something. But it can also cause model convergence problems when we get into the world of longitudinal, because not only are we going to be estimating an intercept as a point, but we're also going to be trying to estimate intercept variance, individual differences around that point. And if that point is not somewhere in your data, the model may not be able to find it. So I use an analogy to describe this process here. And it's the idea of a map. So let's say that you head to the airport. You have to make a connection somewhere, and you're hungry. You have enough time to go get some food. You find a map, such as this one. Does anyone recognize this map? Anyone know what airport I took this from?
Is it Detroit?
Nope, but it is a Delta hub.
Atlanta.
It's Atlanta, yes. So let's say that I'm in Terminal B in the ATL and I'm hungry. and I find a restaurant that I want to go to. What's the first thing that I need to know in the map in order to find that restaurant?
Where you are?
Yeah, where am I? And then where's the restaurant? And then how do I get to there? And that is almost always given to you as a star that says you are here. So in your data, think of the intercept as the you are here sign that everything else is relative to. You have to know where you are to be able to talk about whether you should go to the right or to the left or to the north or to the south or what have you. So if you think about the language that we use to describe results of predictors. So let's say that I'm looking at the results of a relationship predicting writing ability from mathematics ability, and here's my scatter plot, okay? What's the language that you use to describe a slope is, say, as it's the change in y for a 1 unit increase in x, right? Well, what if the intercept in my model is over here? Can you see my cursor? Up here in the right-hand corner?
Mm-hmm.
If the intercept is over here in the right-hand corner, does it make sense to talk about what happens as math increases? No. If you're here, then math can only decrease, and writing can only decrease. Otherwise, if you forget to center math, let's say that you don't have a value of 0 that means something besides 0, and so actually you'd be clear over here somewhere. You would be trying to predict the writing score for someone with absolutely no math ability, which may not even be possible for the test. So you're not even in the map. You're like out in the parking lot somewhere trying to figure out how to go get yourself some lunch. That's not helpful. So the intercept is the you are here sign that allows us to say relative to that point, we can talk about what happens as x increases or x decreases, and then we put in other variables as well. So there's no wrong way to center, but there are weird ways in the sense that your intercept needs to be somewhere in the map of your data for it to make sense. Once you have that point, though, you are not beholden to it in terms of predicting model outcomes. So you can ask the program to give you predicted intercepts at any point in your data. And so you know of this in the context of predicted outcomes. So when I say predicted intercept, another way of saying that is a predicted outcome or a conditional outcome. All of those words mean the same thing. The intercept itself, the fixed intercept, is a very specific point dictated by the scale of your predictors, but the model tells you what the intercept would be at any other point as well. So I'm going to teach you another piece of code here to get these types of predictions, what's known as an estimate statement in SAS. This is called test in SPSS, Lincom in Stata, new in M+, and I can never remember what it's called in R, but I know they have them. Does anyone know what I'm talking about off the top of their head? No, I know you'll recognize it once I start describing what they do. But in these statements, if you're trying to predict an outcome, you must have the intercept. The variables are going to sometimes refer to their predictor values and sometimes refer to their betas, depending on what is being estimated, and that is the trickiest part of getting these right. If you don't have any interaction terms, the variables in these commands always refer to their betas. It's only in the case of interaction terms that can change. The default for continuous predictors is 0. The default for grouping variables, which we'll talk about next, varies by program. So in modeling continuous predictors, so when I say continuous, I mean quantitative, things for which you want a slope to describe the effect of that predictor on the outcome. We will center the predictors such that 0 means something. Typically, people talk about this as grand mean centering. That's fine. You can pick the mean of the variable as your centering point. I tend not to do that. I tend to pick some meaningful value that's near the middle because it's then easier to think about that. Just as an example of this phenomenon, let's say that I have something like years of education as measured in adults. If I ask people, what is your average number of years of education, the mean for the sample might be something like 14.67. But there is no such thing as a person in my sample who wrote down 14.67 years of education. I can almost guarantee it. People probably wrote down things like 12 years if they graduated high school, or 16 or 17 years if they have a bachelor's degree. So rather than picking average education as 14.67, which doesn't actually refer to a person in the sample, it might make more sense to talk about the reference point for the variable as, say, someone with a high school degree. Because average education is a sample-dependent quantity. It could be someone with a bachelor's degree in some sample. It could be someone with 8th grade education in another sample. So making the reference point a number in the scale of the predictor that people can relate to makes your results easier to track. If the scale doesn't really have any meaning, then a number in the middle that's a round number can make it easier to convey your results. So here's what it would look like then in terms of how to request predicted outcomes with these estimate statements in the context of centering. So note that I have a regression equation here, so this is still just general linear model, one outcome per person. So y for each individual, since I have only one y, I have only one e. Each person has an x1 and each person has an x2, so they get I subscripts. The betas do not have any subscripts because everyone shares them. Likewise, my centering constants of 10 and 5 do not have subscripts because everyone shares those. So in this case, I am redefining x1 as a new variable for which 10 is 0. So 10 is my new intercept, my new UR here sign with respect to x1. 5 is the UR here sign with respect to x2. So if I create those two new variables in my data set, I've labeled them as x1c and x2c for demonstration purposes here. Then here's an example of how to ask for information about them. In requesting this word solution, that gives me the univariate wald test for each of these predictors. So I get the test of x1 and the test of x2 as separate unique effects. Their joint test for whether it results in a significant model as in terms of R-square. That's the contrast statement right here, where I have a 1 after each of these variables referring to each of their betas. And then here are some examples of how I would request predicted values. So the first line here, the first estimate statement, is actually redundant and is included here only for demonstration purposes. How would I create a predicted outcome if x1 is 10 and x2 is 5? Well, that is the definition of the intercept. The intercept is when all of the x's are 0. Given my centering, that happens when x1 is 10 and when x2 is 5. So that's why when I write out the estimates that are going to give me this predicted intercept, I'm referring to the betas. So I have intercept 1, that means start with one value for beta 0. Whatever that model said it's going to be, give me that. Because I'm filling in a 0 value for x1c, and because I'm filling in a 0 value for x2c, all this is going to give me back is the beta 0. In contrast, the other lines are asking for what the intercept would have been had we used different centering points. In other words, how does the model create a predicted outcome for any combination of x1 and x2? Well, if I want it for x1 equals 8, I fill in -2 for the value that is to be multiplied by beta 1. If I want x2 equals 4, I fill in -1 for the value that is to be multiplied by beta 2. And so even though I've decided that beta 0 is specifically when x1 is 10 and x2 is 5, this allows me to create a predicted outcome for any combination of x's. And it will give me not only the prediction, but its standard error, from which I can then make plots and such like that. So is this something that someone has taught you how to do up to this point? If the answer is no, then that's okay. If the answer is yes, then that's okay also. I just want to know.
We did it in correlation regression class by Dr. Espo.
Okay. Did you do it in software or by hand?
By hand, I think.
Okay.
There was not too much software part.
Okay. So you're familiar with the concepts, you just haven't necessarily done it in syntax.
Yes, correct.
Okay, and who's talking? This is Ori?
It's
Or
my.
Ishmael. Okay, Ishmael.
Yeah.
I'm saying it wrong, aren't I? Okay.
It doesn't matter.
It does matter. I'm trying. Maybe by the end of the semester we'll get it right. All right, so that's your perspective. Who else wants to tell me? Have you done this before?
I think everyone in our program did it in correlation regression class.
Okay, but by hand and not by software.
Yeah.
Yeah, we were taught about the concept of centering the predictor variable.
Mm-hmm.
Yeah, but not in the software.
Not in the software. Okay, that's fair enough. All right, go ahead.
Remember now, there was an exam from SPSS, but it was not necessarily done in the software. He just showed some examples during the class, but we did not do it actually in the discussion part.
Okay. The good news is that if you wanted to create predicted values for everyone in your current data set, there's like 6 letters you have to type to make that happen in any software package. So you will see examples of that throughout the semester. This is just getting you used to the idea of estimate statements as creating model predicted fixed effects, which is what this is. It's another version of the intercept besides the beta 0 specific one that you've defined through centering. SPSS, by the way, their mixed package does the same exact thing using test, but their GLM package does not. And that might be one of the reasons why he didn't show you it, is if he was using the GLM package. To the best of my knowledge, it can't do this with these types of statements. So, all right. Any other comments before we move on? All right. So before we actually, no, one more time. We'll do this here. Categorical predictors. Yeah, let's do this. So you have 2 options in how you specify categorical predictors. So these are grouping variables. You can either set up the codes yourself or you can ask the software to do it. So there are pros and cons to either approach. I'm going to have examples using one or both throughout the semester, so I want you to be familiar with how this works just in the context of linear models before we start tacking on the harder longitudinal stuff. So just to start then, how would this look if you are denoting the effects of a grouping variable yourself? And I'm guessing you would have talked about this in correlation and regression as well. Some group has to be the reference. You get to pick it. They're going to be a 0 on all of the codes that follow. And the way that I typically set up my own grouping variables is what I call dummy coding, or what's known as reference group coding. For example, if I had a binary variable that happened to be gender, somebody's got to be the 0 and somebody's got to be the 1. So it could be 0 equals men, 1 equals women, or vice versa. There's an alternative that I typically do not like to use, which would be plus or minus coding. This is known as contrast or effects coding. Note that I have plus and minus 0.5 here, as opposed to plus or minus 1. Plus or minus 1 creates its own problem that a group difference is actually 2 units, not 1. So the slope that you get is actually twice as big as it should be, which can be confusing. But I typically do the dummy coding approach. So here's what it would look like as an example with 4 groups. So let's say that we have a treatment group variable, this is slide 25, where I have one type of control and then we're contrasting 3 different treatment types. So there's treatment 1, 2, and 3. To set this up myself, I need to create 3 different variables to represent the 4 different groups. That's why earlier when I had this example in talking about omnibus F-tests, it's a 3 degree of freedom test to test the omnibus main effective group if you have 4 groups. It's 3 pieces of information it needs to do this, and from that it can figure out the missing 4th. So let's say that I denote the control group as the reference. So I would compute 3 new variables. I'm calling them D1, D2, D3, where control is 0 on all 3. If it's group 1, then D1 is 1, If it's group 2, then D2 is 1, and if it's group 3, then D3 is 1, but otherwise it's 0. And once you put all 3 of these variables in the model, each then represents its specific intended group difference between control and each of the 3 treatment groups. So does this look familiar?
Yes.
Yes. Good. So the only way really that you can screw this up is to not put all 3 in. So for example, if you have a model statement that looks like this here, where y equals d1, well, if you only have d1 in the model, if you look at what d1 contains, it would give you the difference between the treatment 1 group, which is where the 1 is, and the mean of the other 3. Because the other 3 are all 0, there's nothing to distinguish them. So it will only be D1, meaning the difference between control and treatment 1, if the other 3 dummy variables are in the model. So the correct way to set it up then would be on the bottom statement here, model y equals D1, D2, D3. And that will give you the intended control versus 1, control versus 2, control versus 3. So now my question is, did anyone teach you how to get the missing comparisons? Let me rephrase. If you have 4 groups, how many possible pairwise comparisons are there?
6.
6. How many is the model going to give me? Directly. How many betas are going to give me directly some of those pairwise comparisons?
3.
3, yeah. So I'm missing 3. Did anyone show you how to get them?
I think so.
You think so? And what did they tell you to do? Because it's going to be one of 2 things. I'm willing to guess.
We can either change the reference group, or we can plug in numbers to do some arithmetics to get a
like grouping the slope and the intercept together for different groups.
And so you can figure out what the group difference would be for the non-intended reference groups, right? But how do you get a standard error and a p-value for that? One way to do it is to change the reference group. And that's what I was taught also, by the way.
I think that's the quickest way to do it.
Oh, see, and I'm going to go ahead and disagree with you there, because I'm going to teach you something faster.
Okay.
Does that sound good?
Yeah.
Estimate statements. So here's what it looks like then. So this part, I'm guessing, is where you're familiar with. How does the model tell you what the mean is going to be for each group? So if this is my model here with my 3 dummy codes for the group differences relative to control, then beta 0 is the control group mean. Beta 0 plus beta 1 is the mean for treatment 1 whenever D1 equals 1. Beta 0 plus beta 2 is the mean for group 2, and then this is the mean for group 3. Right. So we know from this output, by default, whether D1, D2, and D3 are significant. We know whether control versus each of the treatments is significantly different, but we don't know the implied differences among the treatments. Here's how we get them. The math is simple. If we know what the mean is for each of the groups, then we can figure out how the betas tell us the mean differences. The first 3 lines here on slide 27 tell us what the model is designed to give us directly. Beta 1 is the difference between control and treatment 1. Beta 2 is for treatment 2, and beta 3 is for treatment 3, each versus control. But I can do the same logic to figure out what the implied group differences are. So if I know that I have treatment group 2 is given here, and treatment group 1 is given here, the intercepts drop, and I'm left with beta 2 minus beta 1 is the difference of treatment 1 and treatment 2. Treatment 3 and treatment 1 is beta 3 minus beta 1, and beta 3 minus beta 2 is 2 versus 3.
This is what I was talking about.
Yeah. So you can figure out what the difference is, but just knowing the difference doesn't tell you whether the difference is significant. All right? Because you'd have to figure out what the standard error is also.
We can have follow-up or something like that.
Uh-oh, baby's mad at you. I hear him in the background.
Yeah, I'm sorry.
Yeah, he's like
crying there.
Yeah, poor thing. He's like, "Hey, I'm hungry."
I'm gonna mute my.
No worries. I'm a mommy. I'm programmed to hear such things. I wish my son still had the same 4 basic things that would make him happy. Food, diaper, sleep, hug. But it's not quite that simple anymore. But so yes, we can figure out that. I'm sorry?
They hugged him. I think he's silent now.
Okay, yeah. I need a hug. Okay. All right. I need a hug too. Let's see. All right, where was I? All right, so differences. So we got to do the standard errors. Yeah, so doing the math for this is possible, but it's super annoying. And it gets even more annoying to the extent that your model is more complicated because what goes into the standard error changes as a function of whether it's a single level analysis, multi-level analysis, and what level the predictors are at. So here's how to do it in code where it will do the math for you. So first off here, it's the same model. So I would call this an ANOVA. That's exactly what I would call this, even though I'm using a mixed modeling software algorithm. It's REML, so it's the same thing as least squares, and the only predictors I have in here are my 3 dummy codes for group differences. So the first line here on slide 28, this is my contrast statement for my omnibus F test. So this is what is normally provided by default if you tell the program that your predictor variable is categorical. Here's what it's actually doing. It's creating a 3 degree of freedom test of whether there are any group differences across the 4 groups that are significant. So in this case, I've labeled this omnibus F test, but can anyone guess what I could also have labeled this command? This F test is going to give me something else too. Think about this in the context of what if I called this a regression? What have I just asked for? Nobody knows? No guesses? Okay, I will tell you then. I could also have called this the model R-square F test because D1, D2, and D3 are the only things in my model. So if there is a significant omnibus main effect, there is a significant R-square. The next 4 lines then are asking for means for each group. So there's the control group, which means give me 1 beta 0, and the control group is when the other 3 dummy codes are 0. The mean for treatment group 1, I need 1 beta 0, and then I need 1 beta 1, and I don't need any beta 2s or beta 3s. For treatment 2, I only need 1 beta 2, and for treatment 3, I need 1 beta 3. So the intercept shows up in all 4, and then the selective groups then turn on as a function of which dummy code should be active. The 6 possible group differences are then given in the next 6 lines. So the first 3 of these are not actually necessary because the model's already going to give them to me, but I put them here so that you can see the logic. So if I want to know the difference between control and treatment 1, that is what D1 is measuring directly. Control versus treatment 2 is D2 directly, and control versus treatment 3 is D3. Now, if I want to know the difference of the difference, so if I want to know T2 versus T1, I can literally take the T2 line right here and subtract the T1 line of code, and that difference shows up right here. D1, -1, D2, 1. That is how I tell it to take beta 2 minus beta 1. Likewise, T1 versus T3 is -1 for a T1 and a 1 for D3. And then 2 versus 3 is -1 on D2 and 1 for D3. So to get all of these differences would have required re-estimating the model another 2 times. The first 3 differences are given directly when the control is the reference group. The next 2 differences could be given if I switch the reference group to T1, but then I'd have to re-estimate the model one more time with the reference group as either T2 or T3 to get the last one. So who said earlier that changing the reference groups is going to be faster?
Me.
So now what do you think?
Yeah, I think this way is more efficient.
I think it's more efficient too, but what if I could tell you I could make it even faster?
Oh.
What do you think? Do you think I can do it?
I don't know.
Yeah, I can do it. Because all of this coding is helpful for pedagogical reasons, but it's absolutely not necessary because there is a faster way to ask for all of this information. It is what's known as denoting the predictor as categorical. So when in SPSS, this is a by option. In SAS, it's called class. In Stata, it's called I-dot. And in R, I believe it's known as making it a factor variable. Does that sound right? Yes. Okay. Yeah, I'm a novice in R still, so that's what that's making sure I'm saying that right. But this is where you let the program do the coding for you, and it anticipates that you're going to want to have all of these differences. So when the program does the coding for you, it decides who the reference group is going to be, but that solution typically is not something that you're even going to want to look at because all of the group comparisons of interest are going to be elsewhere in the output. So the last group is the reference group in SAS and SPSS. The first is the default reference group in Stata, and this process of denoting these predictors as categorical is not something that is currently available in M+, by the way, which is an absolute bummer. But here's what it would look like to let the program do the work for you. So on slide 30 at the top, the 1, 2, 3, 4, 5 lines of code that are right here, there's 2 main differences. So the procMixed line is the same. Rather than D1, D2, and D3, we have replaced those references with the original grouping variable, which is called treat group. Y equals treat group. Now, if you just had y equals treat group, it would try to put a slope through it. And so to prevent that, I have added treat group to what's known as the class statement. Class stands for classification. So class is how you denote treatment group as a grouping variable, as something to be coded for separate group statements. Then this magic line right here, the last line, LS means stands for least squares means. If you list the variable for which you want group specific means, and then after the slash is where you list options. Can anyone guess what diff equals all gives you?
All kinds of differences. 6.
Yeah, still 6 of them. And what if you had 10 groups? However many group differences 10 would be, right? Diff equals all. How many?
45.
45.
45. Excellent. You guys are much better at math than I am, clearly. I was just going to go with a lot, but yes, 45. So yes, you can get all possible differences. The default here is no error correction of any kind. That's not something that I worry about and believe in. I'll elaborate my beliefs on that later in the semester, but just know that if you want to have some kind of experiment-wise error correction, you can add those options here next to diff equals all, and it will adjust your p-values for those. So what these two statements together, this class treat group and this LS means treat group, what it's doing behind the scenes for you, I wrote out by hand here all of these statements. So first off, LS means with the variable is going to give you the group specific mean. So to get that manually, it would look like this. You need one intercept, and then note after treatment group here, there's spots for 4 different values. That's because SAS understands that when it reads your data, that treatment group can take on 4 different values. And it goes in numeric order if they're numbers. If it's actually a string variable, or if it has formatted labels on it, it goes in alphabetical order. So you have to know what the order of your variables is to know what pattern of zeros and ones makes sense here. So this is just in the order in which it's coded 0, 1, 2, 3. So here's 0, 1, 2, 3. So the LS means part gives you the specific means. All possible mean differences then are listed here on these estimate statements. And the rule here is that each of these lines has to sum to 0. So you can do -1 and 1, and that compares the two groups for which you have an integer. The groups with zeros are then left out of the comparison. It then also gives you via contrast the same omnibus degrees of freedom f-test that is either your omnibus main effect of 4 groups or the model R-square in this case, since it's the only predictor. And here's what the contrast entries would look like to do that. So the thing to note here, all you have to do is list 3 of the possible pairwise differences. It doesn't matter which 3, because 3 is all it takes to duplicate the other 3 as linear combinations of those. Does that make sense so far?
May I ask a quick question?
Please.
Yeah. So, for this new code, so is that like the data set changed from the previous?
The data set hasn't changed.
So is that like for the okay, here like we only have the outcome variable and the indicator for the group.
Mm-hmm.
Is that so for the previous one is, I mean, seems like we have like for each treatment. Is that?
Yes. No? So let me back up here and show you. So I'm on slide 25 here. So this treat group variables in the data set where control is given a value of 0, treatment group 1 is 1, 2 is 2, and 3 is 3. So we have 2 choices in fitting the effective group. We can either work with this treat group variable and tell the program that it's a grouping variable, in which case it does all of this, creating the contrasts, figuring out what the pairwise differences should be, and it does it all for you.
So can we go back to 2 slides?
Sure.
So here, like the model is y equal to d1, d2, d3.
Mm-hmm.
So I'm just feels like there are like multiple columns.
Mm-hmm. Yes, because each D1 and D2 and D3 is a series of dummy codes that are either 1 or 0 depending on which group it is. Yeah.
Yeah. And the second one where like the model is y equals to the treatment group.
Mm-hmm.
It seems like we now we have different levels for that one predictor variable.
It's what ends up happening is that when it says y equals treat group, what it's actually doing is making this same model. The difference is in the definition of what D1, D2, and D3 mean, because when it makes the demicodes for you, it makes the last group the reference.
Oh, okay. Yeah.
So what D1 would mean is if it's the first demicode, it would be control versus 3. D2 would be 1 versus 3, and D3 would be 2 versus 3.
Mm-hmm.
But in terms of needing 3 columns and 3 variables to fully represent the 4 group differences, it's exactly the same. The question is whether you're making D1, D2, and D3 and then going through all of the code to explain to the program that those are groups, or whether you're letting it do it.
Okay. Yeah. Okay.
So this way of D1, D2, D3 is useful when you're teaching people what the program is actually doing when you just say y equals treat group.
Okay. Yeah. Okay, got that.
So this y equals treat group paired with class treat group and Ellis means treat group generates all of the rest of the stuff on this page.
Mm-hmm. Mm-hmm.
That's what it's doing for you.
Mm-hmm. Yep.
And so this omnibus degrees of freedom test here, you only have to list 3 of the possible pairwise differences, and that is your omnibus test of 4 groups. And this, by the way, is why I don't get super excited about controlling type 1 error for pairwise contrasts. That was something that was, drilled into me way back when. Whenever you have an omnibus main effect, you have to correct your pairwise comparisons for type 1 error. Does that sound familiar?
Yeah.
Yep. Okay, see, I think that's bullshit. And here's why. Type 1 error at the conventional alpha level to me, right, 5%, it means 1 in every 20 value, and 1 in every 20 p-values you stare at is wrong. Okay. Where those p-values come from is arbitrary. So just as an example of this idea, if we had set up the model this way with D1, D2, D3, the 3 p-values that show up by default on my output give me the treatment versus control distinctions, right? If I then wanted to get the other missing 3, I somehow am supposed to treat those differently just because they didn't get provided by default? That doesn't make any sense to me. And if I had recoded my reference group to be one of the other groups to get the missing ones, then those are the model provided effects, and I'd have to work backwards algebraically to get the other missing ones. I just don't make a distinction between the p-values that are provided by default on the output and the extra ones that I have to ask for. So it's not that I don't believe in type 1 error, it's that I don't believe in differential type 1 error as a function of syntax. If there's 6 possible comparisons, then 1 out of 20 is a type 1 error. So that's my philosophy. I could be wrong, but that's why I can't get too excited about that. One last thing here, this type of letting it do the coding for you also gives you some flexibility in making up other group comparisons that aren't just pairwise. So for instance, on the bottom of slide 30 here, let's say that you had a hypothesis of just is doing any treatment better than control? That's a reasonable question to ask. So in that case, you might want to get the mean across treatment groups. That's what this second to last statement here gives you. To do that, we would have one intercept, and we would divide the 3 ones by 3, which effectively says make the mean 1/3 equal to each of them. And then do the same thing for the last line, which contrasts the control group versus the average of the 3 treatment groups. And so if you have non-whole numbers like that to be able to sum to 0, you can use this divisor thing to be able to do that. So letting it do this treat group coding for you is advantageous when you have hypotheses that involve combinations of groups and not just pairwise groups. So, all right, so that's my summary slide here. How are we doing so far?
Good.
Good?
Yeah.
Anyone not so good? All right, well, If we're not so good, then that's, oh wait, do I want to keep my ink annotations? No, I didn't even know that was a possibility. Huh. We have just like 5 minutes left here. We can get started with example 2, because this is going to go real quick. I just wanted to make sure that you've seen some examples in here. So I'm looking at example 2A. Should look like this. This is coming straight from chapter 2 of my textbook.
Excuse me, can you open the 200 office? I forgot to bring my ID today.
So we can do just a few of these models, and then we'll pick up with this next time. Does everybody have this in front of them? Or my version anyway?
Yes.
Yeah? Okay. So the story from this fictitious data set, based on a real one, but I made it up so that it would cooperate with me. We're examining older adults, predicting an outcome that's known as cognition. So it's a test measuring crystallized intelligence. We're using chronological age, which we're going to center at 85 years, which was near the mean for this sample. Grip strength is another predictor, which is a proxy for physical functioning. It's going to be centered at now 9 pounds per square inch. Gender, with men as the reference group, and there's also a 3-group variable. Because this is the baseline observation of a longitudinal study. Some of the folks in the study have already been diagnosed with dementia, some are eventually going to be diagnosed, and some are never going to be diagnosed. And so that's the future dementia status of none equals 1, 2 equals future, or 3 equals already current in this sample of 550 people. So just reviewing how to get stuff into SAS. I have defined a variable called file save. So this is like, file save is my generic one that I pick most often, but this is analogous to SAS path or else path in the Making Friends with SAS class. So this is the path that goes to the files for this example. I have also defined a SAS library equal to the value of this place, so that file save is where everything is, both the SAS files and the non-SAS files. Data is make me a new data set in the temporary work directory called chapter 2 from set the location file save and pull in the SAS file called chapter 2. So on the course website, by the way, next to my handout, there's a link to all of the SAS files. So you have the data, the syntax, and the output so that you can run things yourself and verify the results in SAS or using your program of choice as well. So first off is creating new predictor variables for age and grip strength. On the left to the equal side is the new variable. So I'm creating a variable called age 85. It is coming from a variable called age minus 85. So here's a convention that I follow in almost all of my examples. When I center a predictor at a constant, I put the constant in the name. That way I can remember where it's centered at. So age 85 then is the new version of the predictor in which 85 is 0. Grip 9 likewise is the new predictor for grip strength, which is centered at the original grip minus 9 pounds. And I have labels for all of these things down here. We had a gender variable already in the data set called sex MW. So for sex, men, then women. 0 is men, 1 is women. And then here are dummy codes for the 3-group dementia variables. So we'll show you how to do the manual dummy codes, and then we'll show you how to let SAS do it the easier way. So here's some descriptive output for the sample, just so you get a sense of what we're looking at here. So age varies from 80 to about 97. Grip strength varies from none all the way up to 19 pounds per square inch, and information test goes from 0 to 44. The sample is 41% men, and in terms of dementia status, 72% of them have none. Another 20% or so are going to be diagnosed at some point during this fictitious study, and then the rest already have been diagnosed. The current group is the smallest. So, all right. One model to look at, and then we'll adjourn. The empty model. Do you remember what the word empty model means? The phrase, I should say. Anybody?
Like the mean?
Empty means, the phrase empty means the only thing in the model is the grand mean because there's no predictors. This is something you would never do in a regression context, but it is always going to be the first thing we do in a longitudinal context. So the model itself looks like this. Cognition for each individual equals beta 0 plus E. In other words, we are just trying to find out how much variance in cognition there is at all. So model here equals nothing. Nothing before the slash. That's how you know that it is empty. On the procMixed line, in addition to method equals REML that gives us least squares in the context of complete data, there's a couple other options that will show up as useful in the future in terms of putting in our output. We can ignore those for right now. Here is the output. I use SAS listing output because it's easier to paste into my handouts. When you run these same things, it will show up looking like this. This is their default HTML output called HTML Blue. It's harder to paste into handouts, and so I tend to use the old school output for my handouts here. But I just wanted to point out two numbers here. So it read in all 550 observations. In terms of the parameters in this model, there should only be two, right? One of them is beta 0. And the other is not E, but the variance of the E's across people. So the variance of the E's across people is given in this table called covariance parameter estimates. It's 120.76. And you'll note that that variance should match. If I took the standard deviation for cognition and squared it, that should be the variance. So it's just spitting back how much variance is in the outcome to begin with, 120.76, as well as the solution for fixed effects. There's only one right here. This is the intercept. And so that we can get going, who wants to tell me quickly what this 24 means?
The grand mean?
There you go. Grand mean. I'll type that here. Grand mean, because, capital letters, why is it the grand mean?
Because grand mean is the only effect we are modeling in that model.
Yep, because there are no predictors. Oops. Grand mean only. Yep. If you know nothing else about a person, your best guess for their outcome is the mean. So that's where we're at. So we will pick up with the rest of this handout next Tuesday in person, I am hoping. I will let you know when homework 2 is ready. It will closely follow this handout. So we'll finish this next Tuesday, and you should be able to read along in Chapter 2. You can find examples for all of these models in Chapter 2, so even if we don't get through it, you have the text to refer to help, so that you can get started on your homework if you'd like. So, any questions before we adjourn? No? We're good? Okay. All right, well then I will stop streaming and I will hang out for a while if anyone wants to chat during office hours. Otherwise, stay warm, have a great weekend, and I will see you next week, assuming that we can meet in class. If there's any bad weather, check your email and I'll let you know what's going on, okay? Lord help us if we have to do this again. All right, see y'all later.
Professor?
Yes.